Okay, hello everyone. I will talk today about proof of stake sidechains. So this is collaborative work with my colleagues Peter Gaji and Agelos Keyas. So let me start with describing the problem we're trying to solve. So we're trying to solve this problem for, in particular, proof of stake blockchains. So I will focus on this topic in this work. And this will be based on the formalization we have for proof of stake blockchains called Ouroboros. So this is a protocol that is pre-existing, and it's a provably secure proof of stake protocol. So the problem we're trying to solve here is the following. Currently, when people use Bitcoin and Ethereum, they use Bitcoin for a specific reason, and they use Ethereum for a different reason. They use Bitcoin for its safety and relative stability and low volatility compared to, let's say, Ethereum. On the other hand, they would use Ethereum to have feature completeness, Turing completeness, and the nice features of smart contracts. So we see here there's two different blockchains that give different features, and they cannot necessarily be easily combined. In particular, the safety of Bitcoin comes exactly from the fact that its code base is limited and they don't accept too many feature-rich feature requests. So what we're trying to do here is we're trying to create a cryptocurrency in which you will have multiple blockchains, and we would like these blockchains to be able to communicate with one another and exchange information and value. And this is useful because if you have two blockchains, you can have different features on each of them. We start with this blockchain here, which I will call SL for settlement layer, and this will play the role of Bitcoin in the current cryptocurrency world. So it has the Genesis block and a few other blocks, and there's some transactions going on there. And we intend this to be a limited feature blockchain, so not to have many abilities other than moving money around. And we hope people will use this as a savings blockchain where they keep their money safe, but they don't have all the nice features of a smart contract blockchain, let's say. And then we plan to create a network of blockchains. I will just show the case of making two blockchains here. This naturally extends to having multiple blockchains. So we start by introducing a second blockchain, the computation layer. And that's a separate blockchain with a separate Genesis block, and it evolves independently of the settlement layer. And in the computation layer, we want to have feature-rich smart contracts. So the problem we're trying to solve here is how do you move money from the settlement layer to the computation layer, and then how do you move it back? So we want these two chains to work with one shared cryptocurrency, and the users to be able to hold the money wherever they need it to be, either for saving or for useful features. So you can think of the settlement layer as a savings account and the computation layer as a checkings account where you can move your money around more easily and with more features. Right, so what we want to achieve here, and this is our contribution with this, is when you have some money in the settlement layer, you do a transaction here in the settlement layer, and that transaction destroys a coin here in the settlement layer, and then a new coin appears in the computation layer. Then you can move that coin around in the computation layer, and then whenever you want, you can do another transaction over here, destroy the coin in the computation layer, do a transaction to do that, and then a new coin appears in the settlement layer. So with these destruction and creation transactions, you're essentially able to move assets from one chain to another, like that. And of course, this coin here can change hands, maybe be split up or merged into, you can split up a coin into its denominations and only move part of it back, and so on. Right, so if you already have a settlement layer blockchain, the computation layer can start later on. So it can have a Genesis block that starts later on, and this is what we propose in this paper. If you have an existing blockchain, you can do it, you can create a new blockchain that will function as a computational layer later on. Now, the system that I'm discussing here is not applicable to known blockchains such as Bitcoin and Ethereum because they're proof-of-work blockchains. This works for proof of stake. But what we're doing is applicable to the Cardano blockchain, and we're doing an implementation there. So this is our application for this. Right, so what we propose here is to have two types of nodes. The first kind of node is a settlement layer node, and this is a node that only looks at the settlement layer. And then you have a different type of node, a second type of node, which is called the SCL node, a settlement and computation layer node. And these nodes monitor both these blockchains. So if somebody is interested in running on the computation layer, they can look at both blockchains. Their node can connect to both. But if they're just settlement layer nodes, their code is really simple. It only looks at the settlement layer blockchain. Now, the challenge with this is how do we move money in and out when these miners don't necessarily look at both blockchains? Well, moving money out of the settlement layer and into the computation layer is the easy part. You do so this is the life cycle of money, basically. It starts by living in the settlement layer, and the settlement layer is also where the macroeconomic policy of the currency is applied. It's where new coins are minted and so on. And it moves around there. At some point, there's a special transaction that destroys the money, and that's confirmed in the settlement layer. And then a follow-up transaction creates corresponding money in the computation layer. When we move money back in from the computation layer into the settlement layer, this is the harder part. And again, you have the same life cycle. You have some money that lives in the computation layer. It was moved there previously. And then there's a special transaction that destroys this money in the computation layer, and a follow-up transaction within the settlement layer that creates the corresponding new money. The challenge is validating this creation transaction in each case to ensure that the respective amount has been destroyed in the remote blockchain. So this is how it looks. And here's why it's easy to do the one-way thing. And this is one type of node that we propose. It's called a direct observation method. So if you have an SCL node that monitors both blockchains, it's easy for them to verify that this money creation transaction is actually valid. And the reason is because they monitor both these blockchains, they can wait for confirmation on the top blockchain for the money destruction transaction. They wait a couple of blocks for the transaction to be confirmed, and after that is happening, that has happened, then they can verify the money creation transaction at the bottom. Because they connect to both these networks and they monitor both blockchains by direct observation, this is basically trivial. The difficult problem is moving money back because the settlement layer nodes, the SL nodes, even though we want them to validate all the transactions that get confirmed within the settlement layer, they are not looking at blocks in the computation layer. They don't look at all the transactions over there. And we don't want to send them all the transactions of the computation layer or all the blocks of the computation layer. So this is the isolation challenge. We want the settlement layer miners to learn about some information that happens on the computation layer, but without actually connecting to it. And of course, we cannot just send them the transaction because they need to know whether that transaction has been confirmed on the computation layer. They need to deal with blockchain reorgs and so on and so forth. So in order to solve this problem, what we do is we synchronize the epochs of these two chains. And I should remind you, in the Ouroboros blockchain, in the proof of work, the epochs are periods of time where you have blocks, and there's slots of time where in each slot there is an elected leader which is responsible for creating a block. So the leader election happens at the beginning of every epoch, and then the leaders are elected for the rest of the epoch, and then at the end of the epoch there's a new election process that takes place. So given this, we synchronize these periods, these epochs between the two layers. And once we've done that, here's the insight for this solution. So in the computation layer, during each epoch, they elect a small committee of people which will be responsible for passing data to the settlement layer. And they will do that by signing off a certificate that says, here's what happened to the computation layer. But what we want is this committee, we don't want this to be a federation, we don't want this to be centralized. We want this to be representative of the underlying stake. So based on the idea that the majority of stake is honest in the epoch, which is an assumption that the Ouroboros paper makes, the committee that is elected here, we wanted to preserve this honest majority. So this means that we will not introduce any additional security assumptions compared to what the Bear protocol has with one blockchain. Now, in order to do the election, what we do is we take the last 2k slots of the epoch, where this k is the common prefix parameter of the backbone work and the order of Otto's work. It's the number of blocks you need to wait for confirmation. And then we take the last 2k slots of each epoch, and within there we find who are the elected leaders of that. And those are the people, the 2k people, which will be responsible for forming this committee. And for large enough k, the probability that the majority of people within this committee will be adversarial is negligible, provided that we have honest majority in the underlying stake. So this committee, it's important to note that it's not a federation because it changes from epoch to epoch. It's a different committee from epoch to epoch. Okay, so we take the last 2k slots, and these are the people that will be signing off these sort of transfers from the computation layer back to the settlement layer. So here's what happens. You have 3 epochs here, epoch 7, 8, and 9. At epoch 8, we have some transactions that happened, and these transactions are collected into a compact Merkle tree, and then that Merkle tree is signed off by the committee which was elected for epoch 8. So there is 2k signatures in the optimistic case, or if there are some malicious people that are not willing to do the signature, there's k+1 signatures, and the majority of them will sign. The majority of the stake here will sign for the fact that this money is moving away, and this certificate is then posted on the settlement layer blockchain. And in our paper, we have an interesting construction where these k+1 or 2k signatures can be nicely aggregated into a very short signature. And then on the other side, the signature verification is a simple signature verification. It's a protocol that looks exactly like standard signature verification. So you can do that. Now the question is, how does the settlement layer know who is the correct committee? Because the stake on the computation layer evolves with time, and the settlement layer miners do not know how this evolution has taken place. In order to do that, when the computation layer is first created during its genesis block, it has a certain stake distribution. Now that stake distribution is known to the settlement layer miners, so that's the base of the induction. And then as the epochs evolve, the elected committee that voted for which transactions took place on the computation layer also votes on a different statement that says what is the new committee on the computation layer. So the previous committee of the previous epoch in the computation layer, they sign a certificate that says these are the transactions that took place, and this is the new committee for the new epoch. And they make this certificate statement, they post it on the settlement layer once every epoch. Now, one very interesting property that we were able to prove in this paper is the firewall property, and this was one of the original goals of sidechains from the time they were first envisioned. And this is the firewall property, and the idea is if in the computation layer you have some sort of catastrophic failure, for example, there is a catastrophic bug which allows arbitrary money creation, the settlement layer is protected, and this is how we ensure the safety of the settlement layer. The way we do that is quite simple, really. When you have an incoming transaction, an incoming transfer into the settlement layer, the settlement layer node verifies that the total amount that went out of the settlement layer and into the computation layer must be more than what came back in. So you cannot bring more money in from the computation layer into the settlement layer than what went out. The challenge here technically is to be able to prove this. And in order to do that, what we do is we introduce an interesting definition of what it means for a sidechain to be secure. And I have it as an extra slide here at the end. So I'm not going to read that, but I invite you to go to our paper and read this definition. I think it's very interesting because this is something that we recommend that researchers adopt when they want to prove cross-chain transfer security. So we have very interesting formalism and mathematics going on here, and I would be very happy to see that being adopted in other papers. I think it's a very useful formalism. And with that, I would like to show you some more papers other than our currently presented paper here. The rest of the papers that I have here, there's one that was presented in FC earlier this year and a few others from our group, and these show how to do the same thing with proof of work. So actually with this we complete the schema for proof of stake, and now we can do these things for proof of work and proof of stake. And in fact, the scheme that I showed you today, I showed it to you in terms of creating a new blockchain that does this, but in fact it's possible to retrofit existing blockchains both in proof of stake and proof of work to have these kind of features. So to create a new chain that is able to communicate, as well as to build communication between two existing blockchains. So no child-parent relationship between the blockchains, but two existing blockchains. For example, we could interconnect Cardano, a proof of stake blockchain, with Ethereum, a proof of work blockchain, both of which are currently standalone and they don't have this feature built in. So we can retrofit it later on. So this is described in this series of works, and with that, I'll be happy to take your questions.
Thank you very much. Questions? Yes.
Hi, Luke Desitels from Samsung Research America. My question is a little out of scope, so it's okay if you'd like to discuss offline instead.
Okay.
I'm very curious about sidechains and their implications for taxes. I think trying to explain your taxes where you convert from, it's essentially sometimes the same cryptocurrency, there are one-to-one ratios, but sometimes they're not, as you described, like combining proof of stake and proof of work blockchains together. Do you have any thoughts on the tax implications of needing to convert between different tokens?
Yeah.
Very rapidly often.
Okay, so in this construction, the cryptocurrency remains the same between two different blockchains. So that's a very interesting property. If you have a chain that lives on one blockchain, if you have an asset that lives on one blockchain and you move it with this mechanism to another, it retains its nature. So basically this allows us to separate the notion of a blockchain from the notion of a cryptocurrency and have multiple blockchains hold the same cryptocurrency. For example, using this method, you would be able to move, for instance, an Ethereum token from the Ethereum blockchain into the Cardano blockchain, and it would retain its nature. So for tax purposes, you could probably argue that this is the same token. Yeah, it's still on Ethereum, even though it lives on a different blockchain. Yeah.
So when the committee signs off on the destruction of a coin or a new committee, are they providing some sort of Byzantine consensus, or is it weaker than that?
So because the committee, so this is an inductive argument. If the committee of epoch J is honest, then they will sign the committee of epoch J plus 1. By assumption that they're honest in epoch J, they will provide a truthful signature, and then that passes control to epoch J plus 1, and then the epoch J committee is no longer valid, and the epoch J plus 1 committee is now valid. The only assumption we make for that is that there is honest majority in the underlying stake. The way that we do the election, we choose 2K people that are an unbiased sample of the underlying stake, so we can conclude from that that the K plus 1 of the committee, of the 2K people, will be honest. And there's a proof of that in our paper.
We have time for one more question. Yes.
Hi. Isn't the security of the base settlement layer reliant on your top layers now? If the adversary breaks into one of the top layers somehow in one of the committees in one particular epoch, and he manages to send some transactions to the settlement layer, doesn't this essentially corrupt the base settlement layer? In other words, this is like a single point of failure for your whole sidechains.
Yeah, so this is exactly the firewall property that we have. If there is some corruption in the computation layer, the only thing that can be affected are accounts within the computation layer. The settlement layer macroeconomic policy and accounts cannot be affected. And the reason that we're able to achieve that is exactly because the settlement layer miners, they verify that the amount that comes in is no more than what went out. So computational layer people can potentially lose their money if there's a bug in the computational layer. But if there's a bug in the computational layer, the settlement layer cannot have more money imported in than one went out. And so its value will be retained.
So thank you very much.
Thank you.